So we have some momentum problems, and I am going to use these to introduce you to momentum equations, as well as impulse. So in our first one, we have an astronaut that exerts the same force of 20 newtons for the same period of time, which is 0.35 seconds, on two different objects, a 0.73 kilogram flashlight and a 0.28 kilogram screwdriver. The question asks, what is the momentum of the flashlight, what is the momentum of the screwdriver, and how much faster is the screwdriver thrown than the flashlight? So let's first list what we know. We have a force of 20 newtons on both. The time period is 0.35 seconds for both. The mass of the flashlight is 0.73 kilograms, and the mass of the screwdriver is 0.28 kilograms. Let's go to the next screen to figure out the momentum of the flashlight. Now remember, momentum is mass times velocity, or change in velocity, and we don't have a velocity, but momentum is also equal to impulse. So, using our force times time, we can get our momentum. Our force is 20 newtons, the time is 0.35 seconds, so my momentum is 7 newton seconds, or you could also say that as 7 kilograms meters per second. And those are the units for momentum. Now the screwdriver had the same force applied over the same time period, so it's exactly the same answer, 7 newton seconds or 7 kilograms meters per second. So they both have the exact same momentum, but they don't have the same mass. So let's figure out how much faster is the screwdriver thrown than the flashlight. So the screwdriver one more time, the mass of the screwdriver was 0.28, if I remember properly. Let me turn back to my example problem. And yes, so 0.28 kilograms for the screwdriver. Now we know the momentum of the screwdriver is 7. I'm going to use kilograms meters per second, and I'm going to find out its velocity. So momentum equals mass times velocity. This is all for the screwdriver, and the velocity of the screwdriver will equal momentum divided by mass. So we have 7 kilograms meters per second divided by 0.28 kilograms. When we do the math, we have 25 as the velocity of the screwdriver. Now let's find the velocity of the flashlight. Mass of the flashlight was bigger, 0.73 kilograms. Its momentum was the same, 7 kilograms meters per second. And let's find the velocity of the flashlight. So that time VF is flashlight. We'll make that VS for screwdriver. That's our unknown. And our velocity of the flashlight is equal to its momentum of the flashlight divided by the mass of the flashlight. So I added some more variables there, or subscripts, so you can follow what I'm doing. We have 7 kilograms meters per second divided by the mass of the flashlight, 0.73 kilograms. So this time you have 7 divided by 0.73, and we have a value of 9.59 meters per second. Now the question asked, how much faster is the screwdriver going than the flashlight? So I'm going to go up to the top here, and if we take the velocity of the screwdriver, velocity of the screwdriver minus the velocity of the flashlight, we'll know how much faster it's going. So velocity of the screwdriver was 25 meters per second. The flashlight was 9.59 meters per second. So we can see it's about 15, just a little bit more. 15.59 24 is how I would answer that question. Okay, there's your first momentum problem. Let's look at another one. In this example, we have a tennis ball traveling north one fine day, and it encounters a tennis racket and reverses its journey and begins to go south. The racket exerts a force of 24 newtons on the 55-gram ball, and it changes the velocity from 15 meters per second north to 25 meters per second south, opposite directions. We want to know how much does the momentum of the ball change and over what period of time does this change take place. So this time, let's list our variables. We have a force of 24 newtons. We have a mass, notice it's in grams. Let's change that to kilograms. And our velocity initial is 15 meters per second north, and I'm going to say that's in the negative direction, just because, no other reason, and my final velocity is in the opposite direction, so I'm going to make that 25 meters per second. We want to know the change in momentum for A, and B, we need to know time. Those are our two unknowns. So let's go to the next page and do some problems. So, by how much does the momentum of the ball change? Remember, momentum is mass, and I'm going to write change in velocity here. So I'm going to write a delta momentum, change in momentum is equal to the mass times the change in velocity, which is equal to your mass times VF minus VI. Momentum, can be in kilograms. We're going to always keep it in kilograms, so I'm going to use 0.055 kilograms. The final velocity was 25 meters per second, and that was positive. And subtract a negative 15 meters per second north. So notice that sign change is super important. You've got to differentiate between north and south. So for a problem, these guys are going to add together to give us 40, and we have 0.055 times 40. And we have a change in momentum of 2.2 kilograms meters per second. So you could say that's P or delta P. Okay, so now we have that value. Remember, that's the same as the impulse on our tennis ball. And this will help us with the next part of the problem. Over what period of time does this change of momentum take place? Well, if Ft equals change in momentum, remember our force is 24. I'm going to list this for us. 24 newtons. Our change in momentum we just calculated in part A is 2.2 kilograms meters per second. Let's solve for T. T is equal to your change in momentum over force. So T is equal to 2.2 kilograms meters per second, all divided by 24 newtons. Let's look at the numerical value part first. 2.2 divided by 24, and the time period is very small. It is 0.092 seconds. You could use scientific notation. Let's look at the units. A newton is a kilogram meter second squared. So your kilograms go away, your meters cancel, one of your seconds cancel, and you have a second in a denominator that's in a denominator, and that's how we get it as seconds by proving it through unit analysis. I have one more for you, example 3. This time, you're in a snowball fight with your friend, and she has a mass of 45 kilograms, and she's retreating across a frozen pond. She has an initial velocity of 3 meters per second, and she catches a snowball in the back, and it sticks. The snowball has a mass of 0.3 kilograms. and an initial velocity of 20. What's your friend's momentum before catching the snowball? What's the snowball's momentum before finding the child? And what's the final velocity of the child and the snowball combined? So, I don't have room to list everything, but I'll go back and forth. And I changed numbers, so I may have to do that. So, the friend is 45 kilograms, and her initial velocity, I'm going to say friend's initial velocity is 3.0 meters per second. So, what's her initial momentum? So we're not even looking at change in momentum yet. We're going to say momentum is equal to mass times velocity. So 45 kilograms times 3 meters per second, and we have 135 as your friend's initial momentum, kilograms meters per second. So PF. Okay. Now we want the initial momentum of the snowball. And the snowball, just checking my numbers, has a mass of 0.30 kilograms, but it's going a lot faster. The initial velocity of the snowball, do that one more time, pardon me for my sniffle, is 20 meters per second. What's the momentum before hitting the kid? We just need to do mass times velocity. So 0.3 kilograms times 20 meters per second. And as you do your math, yep, it's 6. P equals 6 kilograms meters per second. There's the momentum of the snowball. They stick together, so they experience an inelastic collision. And our last part says, what is the final velocity of the child and the snowball combined? So what's going on here is we have the mass of the child, which I will call m1, and the velocity of the child, m1I, plus the mass of the snowball, m2, v2I, times its velocity, is equal to, they're sticking together, so the two masses combine, and they give us one final velocity. And I'll be giving you a sheet with this equation. So, our first momentum is going to be your friend. Oops, I do that. That's your friend. This is the snowball, and this is the two momentums combined, or the two masses combined. Almost done. What do we have? 6 and 135. Okay. So, oops, here we go. Had a little break there. So, we have the two masses combined. Remember, your friend was 45, and the snowball was 0.3 kilograms. So we're going to add those two together. And we have the momentum of your friend, and we have your momentum of the snowball. So we're solving for VF. So algebraically, it looks like this. So I'm just going to divide both sides by the combined mass. So it looks messy, but it's not so bad to give you the final velocity. So momentum of the friend was 135 kilograms meters per second. Momentum of the snowball is 6 kilograms meters per second. The combined mass of the two is 45.3 kilograms. Do your math, and let's see if we can come out with the same number. Oh, I did something wrong, I see. So 141 divided by 45.3, and I get 3.11 for their combined speed. Goes a little bit faster because the snowball's hitting the friend. gets pushed a little bit by that snowball. Ooh. So that's it for momentum.